All right, today we are diving deep into the heart of modern tech. I'm talking about the semiconductor fab. And believe it or not, there's a crisis unfolding right now, a crisis on an atomic scale. We're going to explore how a brand new kind of AI is stepping in to solve a problem that's just, well, it's gotten too big for our brains to handle. Let's jump right in. Okay, so to really get what's going on, you've got to wrap your head around the scale we're talking about here. It's almost unbelievable. We're literally making computer chips where the circuits, those tiny little highways for electrons, are so small, we measure them by counting individual atoms. Welcome to what the industry is calling the angstrom era. So, what's an angstrom? It's just 1/10 of a nanometer, which is already impossibly small. When you get down to this level, everything changes. The physics of how you build stuff gets weird, and as you're about to see, the way you solve problems has to completely transform. And that's the heart of the problem right there. At this insane scale, the machines making these chips are spitting out an absolute avalanche of data. We're talking about a data crisis that is just too big, moving too fast, and way too complex for any human, no matter how smart, to keep up with. So let's dig into that a little deeper. What does this crisis of the angstrom era actually look like? Why is the data suddenly moving faster than our ability to think? You see, it used to be that engineers were hunting for big, obvious mistakes, like a repeatable error. But that's not the enemy anymore. Today, they're fighting something invisible. It's called stochastic variability. The best way to think about it is pure atomic-level chaos. These are tiny, random, unpredictable defects, things like the microscopic roughness on the edge of a circuit line. And these tiny errors are buried in terabytes of data coming from just one machine every single day. The old school methods, your standard statistical process control, they just can't see the signal through all this noise. And this isn't just a technical problem. This data flood has a real human cost. So let's put ourselves in the shoes of a lithography engineer trying to survive a shift in one of these advanced fabs. And here's the crazy part, the real paradox of the situation. These engineers have all the latest and greatest tools. They're surrounded by sophisticated dashboards and software. But instead of making things clearer, these tools are actually part of the problem. They're just adding to the information overload, creating way more noise than actual useful signal.
This right here, this visualizes the problem perfectly. What you're looking at is a super common dashboard, a tool matching matrix. So you see that red box, the one showing a big 4.9 error between tool A and tool C? That's an alarm. It screams at the engineer, hey, something's wrong here. But that's it. It tells them what is wrong, but gives them absolutely zero clues about why it's happening, or more importantly, what to do about it. It's not an answer, it's just the start of a massive, frustrating scavenger hunt.
And that's where the real pain starts. That vague alarm kicks off something called an OCAP, an out-of-control action plan. And what does that mean for our litho engineer? It means they have to stop everything and start hunting. They're manually digging through a dozen different disconnected systems, trying to read these super dense PDF manuals, and ultimately falling back on what we call tribal knowledge. Just asking the person who's been there the longest. This whole mess, we call it data friction. Now, in a high-volume fab, every single second counts. They have a term for it, golden time. That's the critical window you have to solve a problem before you start losing millions of dollars in product. So every minute that engineer spends on that data wild goose chase, more and more bad chips are being made. The stakes are incredibly high. But what if you could just get rid of all that friction? What if you could cut right to the answer? Well, that's where the solution comes in. We're talking about a completely new class of specialist AI, one that's custom-built for the unique chaos of a semiconductor fab. So when I say AI, your mind probably jumps to something like ChatGPT, right? A general all-purpose large language model, or LLM. But for this job, that's exactly the wrong tool. A fab doesn't need a poet, it needs a physicist. It needs a specific language model, an SLM. Think of it like a specialist doctor versus a general practitioner. This SLM is lightning fast. We're talking milliseconds. It runs securely right there in the factory, not in the cloud. And most importantly, it's been fine-tuned on the actual physics and data of the fab, so it doesn't just make stuff up or hallucinate. This is AI that's grounded in reality. Okay, so let's see this thing in action. Let's look at how a specific language model can take that painful ACAP process we talked about and completely flip it on its head, transforming it from a reactive fire drill into a proactive, intelligent co-pilot for the engineer. It all starts with the alarm itself. Phase 1. Instead of just getting a blinking red light that says temperature high, the AI gives you an alert with context. It says something like, hey, the temperature on track 3 is high, and I found a 95% correlation with an exhaust pressure spike from 15 minutes ago. The problem is probably the exhaust line, not the heater. Just like that, all the guesswork is gone. The engineer knows exactly where to start looking. Now, phase 2 is where it gets really cool. The AI becomes your expert co-pilot. It's already scanned through years of maintenance logs, every manual, every engineer's report to find the most likely fix. It might say, looking at past events, 80% of the time this was fixed by reseating a sensor cable. Check that first. Oh, and by the way, the instructions are in the SOP, Section 4. It's like having the brain of every senior engineer who ever worked there sitting right next to you. And then there's phase 3. Autonomous action. Now, for the simple, low-risk stuff like a temporary network glitch, the AI doesn't even need to bother the engineer. It can safely handle the fix itself, maybe just a quick system reset, and then it simply sends a notification saying, hey, there was a little hiccup, I fixed it, and production is already back up and running. This frees up that brilliant human engineer to work on the really tough, complex problems. So what's the bottom line here? This whole 3-phase approach is a total game changer. The big goal is to slash the mean time to repair, that's MTTR, by 50%. Cut it in half. In a fab that costs billions of dollars to run, that's not just a small improvement. It's a massive win in terms of time, money, and preventing wasted product. But this AI revolution isn't just about fixing things when they break. No, it's also about fundamentally changing how engineers interact with their data in the first place. This leads us to a brand new kind of tool, the conversational dashboard. So forget about clicking through endless menus or writing complex database queries. The idea here is that the engineer can just talk to the data. They can ask a question in plain English, exactly like they'd ask a person sitting next to them. And boom! Just like that, the AI understands the question and instantly builds the perfect chart to answer it. In this case, it's pulled up the overlay error data, and crucially, it's also plotted the maintenance event right on the same timeline. But this is the real magic. It doesn't just throw a graph at you and say, figure it out. The AI actually analyzes the chart for you and gives you a written insight. It connects the dots, pointing out that, hey, the overlay error jumped 15% right after that cleaning on Tuesday. It turns a picture into an answer. So when you put all these pieces together, the smart alerts, the co-pilot, the conversational dashboards, you start to see that it's all building towards a much, much bigger idea, the cognitive factory, a factory that can think. And eventually, a factory that can run itself. And the benefits we're seeing are real, they're tangible, and they are absolutely dramatic. Think about this. A complex analysis that used to take an engineer 4 hours, now it takes 10 minutes. A deep dive yield analysis that could tie up a team for a week, now it's done in an hour. These aren't just small tweaks. These are revolutionary leaps in what's possible. Which really brings us to the final big idea here. For the last century, we've focused on building factories that are really good at making things. But this technology completely flips that on its head. By embedding this kind of specialized domain expert AI right into the bones of the factory, we're creating something new. We're creating a factory that can diagnose itself, learn from its own mistakes, and constantly get better on its own. So ask yourself this: what happens when the factory that builds the products starts to think for itself?